In this video, I describe how to solve a simple maximization problem using geometry. Let us take a look at a simple formulation. In this problem, we have two decision variables, B and M, represents the number of bowls made and the number of mugs made, respectively. And we have an objective function of the total profits. And we have two constraints on the resources. The first resource is clay and the second resource is labor hours. And we have a set of non-negativity constraints. So with this problem, we are trying to decide the optimal combination of mugs and bowls that will maximize the profit within the given constraints on resources. So if you want to copy this formulation to refer back in the future, then it's a great idea to pause the video and copy this down. So let's take a look at how to graph this constraint on clay. First constraint is 4b plus 3m less than or equal to 120. Since we have two decision variables, it is a two-dimensional geometry. The x-axis represents the number of mugs, and the y-axis represents the number of bowls made. In order to draw a line that represents this equation, we need 2 points. You can generate those 2 points as following. First let b equal to 0, and this leads to 3m equal to 120, and if you solve that, m is equal to 40. So we have our first point 40, 0, and if you do the same with m, let m equal to 0, which leads to 4b equal to 120, which makes b equal to 30. And we have our second point 0, 30. So draw a line between these 2 points. The shaded region contains all feasible points for this constraint. So this shaded region is below the line because the constraint is less than or equal to constraint. Let us repeat the exercise for the second constraint. So the second constraint is on labor hours. Like previous case, we need 2 points. So let b equal to 0 in that equation, which gives us 2m equal to 40. So m is equal to 20. Our first point is 20, 0. And if you repeat it with m equal to 0 and 1b equal to 40, which is b equal to 40, 0, second point is 0, 40. Now the next step is to draw a line between these 2 points. And the shaded region contains all feasible points for this constraint. This shaded region is below the line because it has a less than or equal to sign. Now next step is to draw these 2 constraints on the same page. Right? So first constraint on clay, the second constraint on labor hours, right? So the shaded region is common to both the constraint, right? In other words, this shaded region has points that are feasible to both the constraint, hence it is called feasible region, right? The next step is to identify the optimal solution, that is the combination of mugs and bowls that provides the highest profit. I'm going to call this method as brute force method because it doesn't make use of the objective function actively in identifying the optimal solution, but it does help us to get a feel for this problem. So since the objective function and constraints have only linear terms, one of the corner points is going to be the optimal point. So the first step is to identify all the corner points of the feasible region. In our problem, we do not have a whole lot, so it's easy. So the second step is to plug them in the objective function and calculate. Finally, you have to select the point that gives you the highest profit or lowest cost. Right? Simple, right? So let's get to the work. So that's your feasible region, and we have 4 corner points. The first corner point is at the origin 0, 0. The second corner point is 0, 30, and the third corner point is 20, 0, and the fourth corner point is at the intersection of these 2 constraints, and we do not know that yet, right? So which is indicated by the red colored dot. So the next step is to calculate that intersection point. So we have 2 constraints, and let us pick the simplest one and express it in one of the variables. In this case, I'm going to pick the second equation or second constraint, and I'm going to create an equation for b in terms of m. So I'm going to take this equation and substitute in the first constraint. So by doing this, the first constraint will have only terms regarding m, right? So 4 times 40 minus 2m plus 3m equal to 120. Simply rearrange these terms and solve for m. So m is equal to 8, and once you figure out the value for m, plug this value of m back into one of those equations. I'm going to go back for this equation number 2 and substitute and solve for b. So b is equal to 24. So the intersection point is 8, 24. So let us add this information on the feasible region. Now that we have identified all the corner points, let us plug them in the objective function and calculate the total profits. The objective function is 40b plus 50 times m. So when you key in 0, 0, the total profit is obviously 0. Let's go for the second corner point, 0, 30. Objective function value is 1200. That's the total profit. Key in 8, 24. The total profit is 1360. Key in the final corner point. The total profit is 1000. So we need to pick the point that gives us the highest profit, since we are actually maximizing the objective function. So that point in our case is 8, 24. So the optimal solution is to make 8 mugs and 24 balls, which can help us to achieve the profit of 1360, right? So if you notice it, we have never used the objective function as part of the graphical procedure actively. I mean, we never drew an objective function on this graph, other than we used it to evaluate the corner points. So in part 2, I will show how to add the objective function to this graph and how that can be helpful to identify the optimal solution. Hope you enjoy this video. I'll see you in the part 2. Thank you.